All right, so welcome to this example where we are going to, and I am going to show how to apply the disk method into into finding the volume of a solid that is obtained by rotating a region around an axis, a given axis. Okay, so let's now turn over to the wording of the problem right there. And again, another remark here is that this video lecture here, this example is highly recommended to be viewed or watched after you have viewed the video lecture on a general discussion of what the disk method is. Okay, and of course, we should be viewing this video after anyone already had a solid understanding of what the fundamental theorem of calculus is. Okay, and what a definite integral is. All right, so now let's look over to the wording description of our problem right here. All right, so now in this problem right here, let's read the description of our solid right here. Find the volume of the solid that's obtained by rotating about the y-axis. Okay, so rotating about the y-axis, the region that's bounded by. So first, let's understand what the region is. And so my plan for this particular example here is that as we read through the region, as we read through one by one, line by line, the description of the region, I'm going to instantly pull out these graphs right here. So we have the region bounded by the line x plus 2y equals 4. It's an equation. Okay, and then we were told it's a line. So but in the end, it's a graph right here. Any equation in algebra is a graph. Is the equation that represents a graph. And so this equation has a graph. And so now let me switch over to my graphing calculator with decimals right here. And in this empty graphing space, this is the graph in red right here. This graph in red is the graph for x plus 2y equals 4. Okay. All right, and so, but now in the next piece of information, once we've had the graph, we want the region is to be bounded bounded by that line that we have already seen previously, and the x-axis and the y-axis. So the x-axis, okay, bounded by this and the x-axis. So let's have a look at that. So the x-axis is this horizontal line right here, right by the x-axis. So the area bounded by this line and the x-axis. So it must be two areas. So as we ruling down the area, it's not this area out here, but it's this area in here or this other area down here. So that's why we can still see that there are too many possibilities here. So we're going to need to look for the third curve right here to have a clear picture of what our bounded region is going to look like. So in the next piece of information, so here, so it's bounded by the line we have seen previously, the x-axis, now we know, and then it's bounded by also by the y-axis. Okay, so now the y-axis in my graphing space with decimals right here, then this line this vertical line right here is the y-axis. So the x-axis and the line that came out from x plus 2y equals 4. So now with the three graphs here, then obviously the region that's bounded has to be the region where I put my mouse cursor here. It cannot be out here because that's not bounded. It cannot be out here. It cannot be down here. So it has to be somewhere that's inside, that's contained inside. And so there's the area or there's that region that's bounded by the three given curves right here. And so now I am going to give a restricted version because I don't want to look at the whole lengthy graph right here. It's making things more confusing. So I'm going to restrict that line into that part where it's part of the shaded area. So I'm going to restrict that. All right. So this graph right here is this boundary of the region here is the x plus 2y equals 4 equation. This is the y-axis. This is the x-axis. Okay. And so now in that same way, once we have found our region, now let's look at what the rotation requirement is. So this time the wording says right in the beginning, we want to find the volume of the solid obtained by rotating about the y-axis. So rotating about the y-axis. So we're going to take this region right, that we have seen previously and rotating that about the y-axis here. All right, so now that means on my graph right here, I'm going to switch this region over to a 3D view right here. All right, so in 3D view, this is the region right here. It's that line right here, and this is, once again, this is the x-axis, and allow me that this is the best decimals can can do right here in terms of giving a 3D graph. So the x-axis is here, the y-axis is here. So our graph here, even though I'm trying to make that to be in perspective, but it's still trying to reflect that the y-axis is the vertical axis going up, the x-axis is the horizontal one, but we do have an extra axis here for the third dimension. So you don't have to even worry about whether it's a z-axis or whatsoever, but the idea now is that this region is going to be rotated around the y-axis, and so the orientation of the rotation does not matter as discussed in the general discussion. So here let's observe let's observe the final product, the final solid here that's created after rotating this region. And so here I'm going to show that the animation right here. So now I'm going to start rotating. All right, so as we're rotating, and we're going to form into a sort of like a cone right here. Okay, so this is a cone, and now let me change the view a little bit to make the cone a little more the trivial right here. All right, so here's the cone right there. All right, there's the cone right there. All right, so this cone right here, this cone, then is the one that we are going to find the volume for. Okay, so now I'm gonna make a hand sketch right here, because we can, from that hand sketch version, I am going to be able to break down the information. But once again, you have to be able to, even though the problem is not asking for it, but we have to make a sketch right here. So you got to be able to know all of these graphs right here, and be able to identify your own region instead of relying too much on technology, even though I use a lot of technology to demonstrate, but we still need to know how to graph and sketch our own region, and from there we're going to start pushing our imagination. Okay, and so now, once again, in what I see here, okay, the line gives me a shape like that, and then it has some crossing point, here, but then the region we're looking at is here. All right, and then the x-axis is here, and the y-axis is here. This is the y-axis, and this time, according to the description of the problem, we want to rotate around the y-axis. So the y-axis here is the rotation axis right here. Okay, so the rotation axis. So in that way right here, the same generality that I have already pointed out in the general discussion lecture, then we have to place our eyes to look straight. So this is our eyes right here, and we're looking straight down at the rotation axis. So if this time the rotation axis is going this way, my eyes is looking down on top of that. Okay, I'm looking straight down right here. And so now in that way, from where the rotation axis is I'm going to draw a horizontal, I'm going to draw a stripe that is perpendicular with the rotation axis. So all of these details are being discussed and explained thoroughly throughout my general lecture right there, throughout my general discussion lecture. So I'm going to, the stripe has to be perpendicular or 90 degrees with the rotation axis. Okay, so that stripe right here. So in the end, think about the stripe right here. Then in each stripe, as we are rotating around the y-axis, then each stripe gives me a disk. Okay, after rotating the stripe right there. But now once we are rotating the stripe and creating a disk right here, then once again we recognize that we have a cross section that is in a circular disk shape right there, and that's why once again this method here is called the disk method. Okay, and so now and the disk is facing us, and this time with the rotation center is pointing up right here, then our disk is a disk that's being facing up like that, being placed horizontally. Okay, and so in that way, as we are accumulating, you see we can have many stripes here, and each stripe gives us a disk. So we're accumulating the disk in a sense of we're stacking up those disks. Okay, and so using the disk product here, but in the end, what I fundamentally want to introduce, for each disk, we always want to find, and each disk right here, the shape of the disk is the cross section, the shape of the cross section. So we want to find the area of the cross section. Okay, the cross section area. That's the fundamental that I want anyone to catch right here. We want to find the cross section area and multiply that with the thickness of the disk. Okay, any disk there has a thickness. See, this disk here has a thickness, And even the stripe, the very thin stripe, it has a thickness. Okay, and then we're going to be, so the cross-section area times the thickness give us the volume of one thin disk. And now we're going to be accumulating all of those disk volumes from some start to some end, and I will get even more into details with that, but we're going to have to be accumulating from a given start, or maybe we're going to have to find out where the start is to an end right here of the accumulation. That is how we're going to eventually end up with that final volume right there, because again, a definite integral that we're using here is accumulation. Okay, so finding the volume here is done through a accumulation work right here. We're accumulating these disk volumes. Okay, so now, once again, just like how I have explained and gave that advice in a general discussion lecture right there, then the first step, the easiest step, is to identify where our thickness is. We just look right into the way. We look right into the way how our solid is set up right there. So in this way, in the way how our solid set up, then the thickness on each stripe, which eventually become the thickness of our disk right there, how thin or how thick the disk is, that thickness right here is the dy right there. Because for each disk, we place our rotation axis to align with the y-axis, and each disk here come out with a thickness being the infinitesimally small change in the y value, and that's why it's a dy differential. Okay, and so now once we saw that all of that demonstration and the explanation there, then I can start partially completing out our expression here. So with the same integral that we're partially going through, cross-section area, we didn't find a formula for that yet, so let's leave it the same, cross-section area. Okay, but thickness now is known to be a dy. And then, of course, we're going to be accumulating from some starts to some ending of the accumulation. We will find that out later. Okay, so with the start and this end right here. Okay, but now the reason again that I gave this explanation back in the general discussion lecture, but the reason I in my personal experience, I want my student who study with me to find thickness first, because once we found a thickness and know and realize that the thickness is either a dx or a dy, which in this case is a dy, then we're going to know that the function that we are about to set up here, the function that determines our cross-section area, must be a function that is in terms of y. Because for the rule of setting up a definite integral, when I explained this in an earlier lecture about how we're setting up an integral, then the function here has to stay with the variable to be consistent with the one indicated here with the d expression here. So here it's indicated dy. So our function has to be a function of y. Okay, our function has to be a function of y. So now in that way, we're going to look for cross-section area. Okay, and now we have in mind how we need to express the cross-section area. Then, well, area of any circle is a radius, pi times radius square. Okay, and the radius here, allow me to clear out some picture, this picture right here, because it's making it a little too much. Okay, but with all of this representing the area. All right. Then our area here came out from the stripe being rotated that created this. So the stripe here, we already knew it has a thickness. But this in this way right here, look at the length of the stripe, which is now our radius. This is our radius. Okay, this is our radius, but the length of the stripe this time, or the radius, that is being it looks like it's the function. I mean the output of the function in terms of y's. So it looks like as we change a different y value, let's say when we're at a higher y value up here, then the length of the radius gets shorter, or when we stay at a height at a y value that's lower to the bottom side of the region right here, then the length right here come out being longer. So in other words, the radius should be determined as a function of y value, making it, or of the function of y variable, making it consistent with this dy expression. So in that way, now recall again, this graph, this line right here, this boundary has equation y equals, or actually x plus 2y minus equals 4. That's just an equation that gives us this line. So now it is our responsibility to solve this equation for x here as a function of y. Okay, to re-express this equation as a function in terms of y right here. Okay, so quickly I am going to see that on my scratch work right here, or how about let me move to the other board. So x plus 2y equals 4. I am going to subtract both sides by 2y right here algebraically, and that gives me the x equals 4 minus 2y. Okay, and that is my final expression. One singular x variable equals an expression in terms of y. So this is now a function in terms of y. So that means the area here is concluded as a function of y is going to be expressed as following. It's pi times 4 minus 2y to be the radius that depends on the y value. See how long this stripe is? This radius depends on where we place, on the y-axis, where we place our stripe. Okay, so in that way, 4 minus 2y, that's the radius, and we need to square. And now, ladies and gentlemen, we have successfully found our expression for the area of the cross-section, but we expressed successfully in terms of y variable, making it consistent with this d expression. Okay, so now allow me to write this into the other little space here. Pi times 4 minus 2y squared, because I want to leave all the space here for the next completing part of the integral. And so in my next step, the integral here becomes pi times 4 minus 2y squared times dy. And now my integral keep getting better and keep getting better. Now it's now time to find the start and the end. Okay, the start and the end of our accumulation. Okay, and so again, once again, in my lecture video that had the general discussion about this method right here, then anytime our solid is being rotated around the y-axis, okay, anytime our solid came out from rotating the region around the y-axis, then the accumulation is going to happen from the bottom up. And of course, I'm talking about the method that we're using cross-section here, or more specifically the disk method, because the cross-section here appears to be disk, right? And as we're accumulating these disks right here, then we're stacking up the disk from the bottom up in a way how the picture looks, okay? Or just like that, how this cone right here looks right here. Then think about those infinitely many disks right here. Then we're stacking up from the bottom up, okay? So it looks like now we produce for ourselves another little extra work, and that's the fascinating part about this, that I want to bring it out as an example right here to show you guys that in this problem we were not given directly the low to the high, so we have to either look at the picture or find it out on our own right here. So we just know that start to end makes sense to be from bottom up. So bottom is here. So bottom is here. So it's easy. Bottom, the start of the accumulation is here, easy. That's y equals 0, the bottom. So now go from bottom up, so y equals 0. So this value here, I have to be clear, it's in terms of the y variable, the horizontal line right here. See, this horizontal line is the bottom of our accumulation. Okay? But now, what's the ending one right here? The ending one has to happen at that y value, but we haven't found that yet, and it's not even given. Okay, so that means in that way, on this board of mine right here, x plus 2y equals 4. But in that same fundamental, allow me to swing back to that board again one more time. But we want to find out where that y value is ending our region. That's the top end of our region, the top end of our region. But the top end of our region here came out from where the graph here crosses the y-axis. The graph crosses the y-axis, meaning we're looking at x equals 0 here. X equals 0 here. X equals 0. So x equals 0 means I'm going to substitute x equals 0 into this equation. So 0 plus 2y equals 4. So consequently, from that equation given for the graph, we produce this because we want x equals 0. okay, where that upper end crosses right there, where that graph crosses the upper end of our region, then it has to be x0. It crosses the y-axis, okay? And so in that way, now I can find out what y value that is. It's a 0 here, so it's 2y equals 4, or we're looking at y equals dividing both sides by 2, okay? So we're now looking at y equals 2. That is the ending or the upper end of our accumulation that we're accumulating from 0 to 2 this time. All right, so now we are ready to really complete our final integral setup. The ending of our accumulation here is to 2. Okay, so it's to find this volume, the volume of this cone is from 0 to 2 right here of that function multiplied with the dy. Okay, so all together allow me to write my overall integral here. So, ladies and gentlemen, volume of this cone right here is going to be found by its accumulation from 0 to 2 on the function pi times 4 minus 2y all squared with the dy. Like that. Okay, and in this problem right here, allow me to completely skip the formula, whatever formula you've seen in the textbook. Yes, it's still agreeing with the formula. It's just I don't want my students to focus too much on formulas, because I also mentioned that in the general lecture, if you tie yourself down too closely, okay, or too tightly with formulas, and eventually there will be way too many formulas to know, and that will also become a challenging to know when is to use which formula. Okay, and so there we go. All we have to do now is to complete this, or to finish this definite integral, and that gets us the problem. And so I am going to use the fundamental theorem of calculus to find this integral problem. And so that's why earlier in the beginning of this example, in this video right here, I was saying that I highly recommend watching this after you already knew what the fundamental theorem of calculus is. Okay, and so now I'm going to erase this extra work right here. And so in my next step, I am going to FOIL out, and also in the meanwhile, I'm going to bring that pi right here as a constant coefficient in front. So pi times the integral from 0 to 2 of, and FOILing this out, I'm looking at 16 minus 16y plus 4y squared. Okay, all of that there with the dy. So doing a FOILed out version of that perfect square is going to help speeding up the process right here. And so now here's the step where we can use the fundamental theorem of calculus right here. So FTC, or the fundamental theorem of calculus, says we're going to simply just find the antiderivative of that function. In terms of y, of course, and all of these integral limits now are those values on the y-axis, as you have seen that explanation earlier. So 16y minus, now we're looking at 8y squared plus 4/3 y cubed. That is my antiderivative on this function of y. And now fundamental theorem of calculus say, hey, let's just evaluate this antiderivative from 0 to 2. Okay, and so assuming anyone is already fluent with how to use the antiderivative work, then allow me to skip that step where I show the plugging in right here. Okay, but the final answer here, allow me a second to obtain that final answer. All right, so my final calculation came out to be in exact expression 32 pi over 3, and that is the final volume of our solid right there. Okay, so once again, as a quick checkpoint right here that I have also discussed at the end of the video lecture that has a general discussion about this method right here. But in the end, what we're finding here is a volume. So for volume, the answer needs to be strictly a positive answer, okay? Because it makes completely no sense to have a negative volume. It's some physical quantity that we see, that we can observe, that we can calculate about volume. So it has to be a positive value. And then it's not fun at all to work on something that has 0 volume. And so that's why these kind of problems almost do not exist in our work right here. So we only work with the kind of problem where we end up with a volume being positive. So that's something that you need to check for consistency right here. If for any reason you're carrying out your definite integral work, okay, and come out with negative answer, you got to go back and check your work somewhere because the reason here is that the reason I have to mention clearly, because somewhere I did explain earlier, an integral itself, a definite integral itself, is not necessarily an area or a volume or an integral. Or a physical work problem, but an integral itself is just an accumulation of function value with a d expression. And so integral could be just simply an integral problem. It could be negative, but now when we apply that into finding a volume or an area, something with a physical meaning, then the answer has to be a positive amount. Okay, all right. And so now, before I'm wrapping up, in case anyone is concerning how I got this with the fundamental theorem of calculus, then let me just quickly spend a step, even though you're not required to watch this, to know this, to view this. All right, so from that step, pi times 16y minus 8y squared plus 4/3 y cubed. Okay, all we do now according to the fundamental theorem of calculus, that is just going to be pi times now 16 times 2 minus 8 times 2 squared plus 4/3 times 2 cubed. Okay, that's how I wrote down the substitution, where I substitute 2 into every single y variable here and then subtract. And there's pi, but imagine every term inside my parentheses here has a factor of y, right? It has a variable y variable part here. So when we substitute 0, then it's all going to be a 0 out expression right there. Okay, and so in that way we mainly only need to do this calculation, and that's why you saw that earlier I was just quickly using my calculator for getting the exact answer for that. But once we tear it down to this, then in case anyone doesn't have the advanced technology or advanced calculator, you can still do your math manually and to arrive at 32 pi over 3.